All right. In this short lecture, what I want to do is highlight both the importance and the concepts contained in Hohenberg-Kohn 1 and 2 theorems. Uh, what we know, what the question is being asked by Hohenberg-Kohn 1 and 2, is there a unique relationship between density and energy? Another way to say that would be, is there a unique relationship between the ground state density and a potential? Because you add the potential to the kinetic energy in the Schrodinger equation, and the electron-electron repulsion, whatever, the other pieces, and that determines the energy. So to ask, is there a unique relationship between density and energy, is equivalent to asking, is there a unique relationship between density, ground state density, and potential? And that's what Hohenberg-Kohn 1 and 2 is going to show. It was the central question facing Thomas Fermi-Dirac density functional theory. Was it even valid? You know, we could justify that the Schrodinger equation was valid because you could carry out calculations that agreed exactly with the experiment and continue to get better as you added terms. But here, Thomas Fermi-Dirac theory was never very good. Maybe it was never very good because it was never justified. Well, Thomas Fermi-Dirac theory is an approximation of density functional theory, so better to say, was density functional theory ever justified? And the answer from Hohenberg-Kohn 1 is yes. So the question you might ask is, maybe a given rho can be associated with many energies and wave functions through different potential. And what Hohenberg-Kohn 1 says is rho and the ground state energy are uniquely related, which means that there is some way of taking rho and getting an energy. Sadly, it doesn't identify what that way is, but at least it points to the fact that there is such a relationship. Okay, so the proof goes like this. It's in the book. It's quite nice, but let me just hit the high points. It uses the variational principle. And what it assumes is there are two different potentials that yield wave functions that are different, but have the same ground state density. So that would say there is no unique mapping between a density and potential, because you can get either one of them or more. And what it does is it says, well, okay, there are those wave functions that reduce the density, and they have the same density. I'm going to use those wave functions in the variational principle twice. So in one case, I'm going to say this is the exact wave function and potential, and I'm going to use the other wave function as a trial wave function, and I'm going to get an inequality when I do so. And then I'm going to flip it around. And what you find out is because the density is the same for both those wave functions, that's the assumption you've made, they reduce to the same density. You get a contradiction. Here I've written it as x is less than x. It's that the sum of the two energies for those two different wave functions is less than the sum of the energies for those two different wave functions. It's a proof by contradiction. So if the variational principle is true, it turns out that Hohenberg-Kohn shows that there's a unique mapping between density and potential, therefore density and energy. And that's what we see here. Symbolically, it says that rho determines the number of electrons, the charges on the nuclei, the positions of the nuclei, which determines the Hamiltonian, which determines the ground state wave function, which determines the energy and all of the properties. That being the case, we'll say the ground state energy depends on rho, and we'll break it up into the three terms of interest: the external potential, the internal potential, and the kinetic energy. And what you see is only one of those three terms depends on the nuclei. This is the exact, if you have the exact density, interaction of the electrons with the nuclei. This is the total energy. This piece here must just be in fact, is the kinetic energy plus electron repulsion. And it doesn't depend on what the potential is. You have factored out all the pieces that explicitly depend on nuclear potential here. Now, rho naught is uniquely related to the potential, So there is an implicit connection to the potential here. But whatever this functional is, doesn't contain any terms like this. We call that the Hohenberg-Kohn uh, uh, functional for kinetic plus electron, kinetic energy plus electron repulsion. All right, so what does it do for you? It says there is some unique relationship. Hohenberg-Kohn 2 says, well, if you wanted to look for the grounds, if you had that functional and you wanted to look for the ground state density, the way it works is you insert a density into the exact functional and you get an energy. And then you just use the variational principle. It turns out only if the density you put in is the exact ground state density does the energy equal E naught. So you can just drive the energy down, and you see that E, there's another variational principle application, that E naught is always greater than or equal to, if you use an appropriate density, E of your trial density, which is just the sum of those three terms. This plus this is the universal functional. And so that gives you a prescription for how to look for the best for the ground state density. You would minimize, if you had this, you would minimize it with respect to the density to get E naught. Now, the last section in here talks about the constrained search. And for our class, I don't want you to stress over this too much because it turns out it's not an issue for the way we do things. I don't know if anybody has ever heard the term inside baseball. You know, you can watch baseball, never having seen it before. You watch guys run around and hit home runs and that sort of thing. But at some point, somebody wrote a book that says, well, you don't know how much is going on behind the scenes in baseball. Why it is you take on a 3-0 pitch, why it is you don't steal on a 2-out count or something like that. So the constrained search is really there, but it's fascinating. Embedded in Hohenberg-Kohn 1 and 2 is the thought that the density you are using has to come from a physical potential, one that you could have written down. Now, how do you know that? You grab the density off the shelf. How do I know it came from a potential? And that's difficult. The constraints on that are really, they're hard. In fact, I'm not sure we know all the constraints. What the constrained search does is it says, look, you know, if you do it this way, you don't have to worry about that it comes from potential. All you have to worry about is whether it's an antisymmetric wave function. And that's easy to do. Now it turns out that the way we're going to do things, the densities we're going to construct, all will have come from a physical potential, the way we do the calculations. So that's not such an issue for us, but it's something density functional people worry about. For us, we're not going to worry about it, except if you want to talk about it, I'd be happy to do so. So, with that in mind, I'm going to stop sharing and